Hi, everyone. Thanks for tuning into my presentation. My name is Kristen Oakhorn, and today I'm going to talk about the INSTEP monitoring network, which I've developed during my first year as an NPP, and talk about some of our preliminary findings. So you may be thinking, with the low-cost air monitoring network, aren't there already air quality monitoring networks? Doesn't NASA and the government already have a lot of really expensive air quality instruments that we can use? So the answer is yes, but there's still a lot that we're able to add to those. So on the top in the green, I have some example data of about a month-long period of data from a monitor run by CARB, or California Air Resources Board. And this is the closest air monitoring board for an ozone instrument, the one that's closest to NASA Ames, which is still about 11-12 miles away from us. So the benefit of these instruments that are already on the market is that they're really high cost, so they're very reliable. However, with them being so high cost, there's not as many of them spatially distributed as we would like. So a monitor that's 12 miles away from us isn't telling us exactly what's happening at our site. So there's the beauty of the low-cost monitoring network. Since they're much less expensive, we're able to put a lot more of them out. Although, of course, with them being low cost, the data quality is not always as great. So we do have to do a lot more work on our end to make sure that that's reliable. And then the example data that you see down here is from the INSTEP monitor, which I'll introduce on the next slide. And that also shows ozone, which you see the patterns are quite a bit different, although the concentration range is the same. So that kind of gives you the difference of what the air at NASA Ames is like compared to in San Jose, where the reference grade monitor is. So this is the inside of one of our INSTEP monitors, and I'll introduce INSTEP here as the inexpensive network sensor technology for exploring pollution. So this was originally developed, the platform here, by my graduate research lab, the Hennigan group at the University of Colorado Boulder. And with this, we're able to measure a variety of gas-phase pollutants. So we have two different VOC sensors here. So we use these for different hydrocarbons, such as methane and formaldehyde. We have our ozone sensor here. We have a CO2 monitor, and we also have two additional sensors for carbon monoxide and NO2. And then we also have temperature and humidity sensors, which are important for kind of correcting some of the biases of the low-cost sensors that can happen with outdoor sensing. And currently, this is all logged to an SD card. Future iterations will have telemetry to kind of make things easier on the data collection end for us. So this is the monitoring network that we deployed this summer. We have 7 monitors in the San Francisco Bay Area near NASA Ames. And then we also have an additional 3 with some of our partners outside of Los Angeles. So we want to recognize that while this is a pretty good setup, it definitely is a lot across California that we're still missing, which kind of brings in the need for us to still use satellite data as a complement, where we can kind of look at the entire state and a lot of areas that we're missing as well. So I'll talk about that a lot in our analysis of what the low-cost sensors and what the satellites both can and cannot tell us, and kind of together what pieces we can fill in from there. So I do want to recognize the 2 different color points that we have on this map. So each of the blue ones are co-located with other instruments, most of them spectrometers we can use for remote sensing. So if you're not familiar, think of as upside down satellite, that helps us to kind of look at a wider grid there. So we have the TCON instrument, which is shown in this picture kind of in the middle here, the picture closer to the left, which is on top of the container. And there's actually also a Pandora in this photo as well, in the front near the cones. And then our INSTEP monitor, very small comparatively, is hung from that yellow railing circled in red there. So the TCON measures for CO, CO2, and methane. So we're able to do some comparisons there against our INSTEP monitors. And then the Pandora, which is shown again in the foreground of this picture in the middle, and then on the right of this picture, that is all the way on the right next to our INSTEP monitor. The overlap that we have in pollutants there is NO2, ozone, and formaldehyde. So we're able to do a few comparisons there, having these in a wide variety of locations, as you see here, one in the Mojave Desert at NASA Armstrong, and then this one on the right here is of San Jose State University. So kind of getting a pretty wide range of different environmental locations as well, in addition to those remote sensing and non-remote sensing locations. So I'm going to talk a little bit about some of the initial analysis that we did comparing our instrument with remote sensing instruments. So this is again from our NASA Ames site for ozone, but this time comparing our INSTEP data with the Pandora data that was available there. On the left-hand side here, you'll see data from the Pandora instruments. You'll notice that we only have measurements during daytime hours, and this when the sun is available. And you see right off the bat that they're not super comparable. We have a really different range of concentrations that we see in our ozone data. I'll also mention that these are really different scales. We're looking at a total column measurement for ozone from the Pandora, which is in Dobson units, versus our ground level ozone. We're just looking at ppb. So really not super comparable. We're looking at totally different things. I do want to point out too, we see much larger ranges of concentrations from the Pandora on kind of the outermost columns of each. So for measurements taken at 7 a.m. and also at about 6 p.m. And we do think that that has to do with the solar angle being a bit off during those hours, and that's why we're seeing some differences there. So as we continue into our analysis, we'll have to look at that as something to maybe correct. So from there, we kind of started to think, okay, well, maybe we need to look at a more ground-based measurement from our remote sensing instruments to see how well we're doing in the comparison, because having the two separate measurements kind of gives us some good idea of how the column is representative, but then how can we start to kind of compare the two in a way that's more similar. So here I have data that we have from our monitor at Caltech. So on the top pane here, you'll see a photo of the TCON instrument, which I mentioned is one of our remote sensing spectrometers at Caltech. And then beneath that, we have data from our NASA INSTEP monitor. So our INSTEP monitor is in the foreground of the photo on the bottom. And then you can see behind there that same quad that the TCON is located in, although you can't see the TCON in this location. So just to give you an idea, our INSTEP monitor is actually a bit higher, a few stories higher than the TCON, just based on where the rooftop is. But it is basically right across the street, maybe about 200 feet or so away from the TCON. So they are pretty closely co-located still. So now looking at the actual data. So for the TCON, we have a partner, Harrison Parker at Caltech, who was able to share with us some data that he's manipulated from the TCON to look at just the lower column, the lower 2 kilometers of that data versus the entire column. So it's looking at just the data that is closer to the ground in terms of the whole column of TCON data. And we do see a lot more agreeability between that data and ours. So although they're still a bit different, we are at least seeing the same range of concentrations. So that's a really good sign for us of kind of narrowing down on a closer comparison and seeing how well these two instruments are doing compared against each other. So that was a really promising first step. Some things that we are still curious about in this data are why kind of all these larger spikes, so all of the kind of outliers that show up in this box plot of data from our INSTEP monitor seem to be from about midnight to 8 a.m. So not really when we'd expect people to be up on the roof, breathing near it, or would expect to see emissions from traffic. So we're still digging into that. So the last thing I want to show in terms of data is an inter-INSTEP comparison. So from 2 different INSTEP sites to kind of give you an idea of what some of that is showing us so far. So here on the top again, I have data from the Caltech monitor, which I showed in the last slide, although this time we're looking at CO and not CO2. And then the closest nearby monitor to that is at the Table Mountain facility site, which is ran by JPL, but is not at the JPL site also in Pasadena. It's up in Table Mountain, up in the mountains, about 50 kilometers away from there. So looking at both of our INSTEP monitors, we definitely see some pretty big shifts. The concentration range is pretty different. The amplitude is pretty flat at Table Mountain, although we do at least compared to Caltech, although we do see a lot of variability still throughout the daytime. Whereas at Caltech, maybe the range is a bit wider, but we're definitely seeing a really different trend there. And we believe that most of these differences are driven by changes in the planetary boundary layer. So as we know, kind of rising during the day and falling at night. So Caltech being inside of the LA basin is seeing the full kind of change there, versus JPL might not even be getting any of the changes from that because it's situated so much higher up. So that is definitely one big part of it. So we do believe that from previous studies that kind of the air from the LA basin during the daytime is definitely brought up to Table Mountain, which is one of the reasons why they've developed that site there to help kind of understand some of the differences there. But I do want to note too, so there is a Pandora at the Table Mountain site as well, which I have a photo here kind of in the middle panel between the data and the map. So I'm not showing data from that Pandora just yet. We're still trying to figure out some of the discrepancies here between what's happening at sites. But I do want to point out that with the Pandora, just looking up and thinking about these differences in planetary boundary layer, when the Pandora is just looking up, it is kind of just looking up at the free troposphere and not really seeing some of these other changes that we're seeing in our ground level monitor from the LA basin air coming in and those different things. So I thought this is a pretty cool comparison so far of kind of what we're seeing from the INSTEP monitors that some of the existing monitoring at each of these sites kind of misses out on. So then I just want to talk a little bit about some of our next steps. So in the short term, we are looking to explain some differences driven by wildfire with these monitors. So fortunately, it's not been the worst fire season in California this year. So the two largest fires in California, the Mosquito and the Fairview fires, are currently still burning and only started in September. So our data is a little bit behind in that sense. So we're just starting to get into analyzing some of that. Like I mentioned, there is quite a bit of machine learning and quality assurance checks that have to go into the low cost sensor data to make sure it's reliable. So we haven't quite gotten to that point in September yet. We also want to compare with other network data. So for example, at Caltech, the CIT AQS data, which is available for quite a few pollutants, will be cool for us to compare data with. And we also have some models that some of our partners at NASA do at Table Mountain facility and also at a variety of other locations that we're hoping to first compare our ozone data with and then hopefully incorporate into some kind of a model. And then one of the last things that we're planning to do in the short term is from each of those column measurements. So like I mentioned at Caltech, going from full column to lower column, we also want to look at ground-based estimates from the existing spectrometers to see how we can kind of use that for even better comparison and use our monitors to validate whether or not those ground-based estimates are accurate or not. And for our longer term goals, like I mentioned, with our INSTEP monitors having the SD card, we are looking to move towards telemetry. That way we can know right away if a sensor goes offline and aren't waiting until I drive out there to go pull data to find that out. This would also enable us to just do faster data analysis if we could just pull it without having to travel everywhere to go pull data. Like I mentioned with the remote sensing comparisons, one of the big goals for this is tempo validation. So once that launches in early 2023, we would like to do the same thing, kind of comparing to the lower 2 kilometer tropospheric ozone product that they'll have available, and also any ground-based estimates would be awesome since that will be on such a higher spatial scale of data. I also think 2 kilometer by 2 kilometer roughly. And one final thing that we're looking into is getting these monitors onto uncrewed aerial vehicle, which we think could be really cool for volcanic emissions and also for wildfire as well, to kind of get a safe way of measuring data that is right near a plume. So that's all I have for us today. Thanks for your attention, and I'll be around for questions. Thanks.